that we're doing right now, I will refer to as vertically simple. And by vertically simple, I mean that you can draw a vertical integration element, which you should visualize just as a rectangle, a very thin rectangle. And it doesn't matter where you draw the rectangle, the upper curve is the same no matter what, and the lower curve is the same no matter what. We'll think of that as vertically simple. So we could, wherever we draw our integration element, aka our rectangle, the y equals 0 is always the upper curve, and this trig curve is always the lower curve. So it's vertically simple. We can use a vertical integration element, which is the same for this one here, right? Doesn't matter where we draw the element. The black curve's always the upper curve. The red curve's always the lower curve. So vertically simple means that we're going to integrate with respect to x. And the way that we remember that the differential is dx and not dy, which we'll see in the next couple slides, when you're thinking about your vertical rectangle, think of the width of the rectangle as dx. So if you have a vertical element, vertical rectangle, think of that width as dx. The height is going to be the upper curve minus the lower curve. So the height of the rectangle is upper curve minus lower curve. Thickness is dx. In a couple of slides, when we get to horizontal rectangles, horizontal integration elements, the thickness will be dy. And then the height is sideways, and we'll have to do a subtraction where we do the right curve minus the left curve. So those are the two types that our two ways that our regions can be oriented. So vertically simple is the more intuitive one. We did one example in total over there. We're going to finish off this one. And so here, the upper curve is 0. The lower curve is this trig curve, and we were subtracting it off. So we have upper curve minus lower curve. So that's the height of the rectangle. The dx is the thickness or the width of the rectangle. So when you look at the integrand, including the differential, that is all representing the area of a rectangle. And the integration symbol is supposed to resemble an S. You're summing up all of those rectangular areas to get a cumulative area. So that's where we were, and then we had to figure out how to integrate this. And there's several ways that we can do it. Almost all of them involve substitution. So we decided to let u be this part, cosine x minus 2. And then we took the derivative and got minus sine x, so the part that's highlighted here, that, and that is all going to be replaced with du. Could you have done something different? Yes. You could have distributed the sign. That's totally legit. You could distribute the sign. You would then have one integral that would be a positive 2 sine x, which you can integrate immediately. But then you would also have a sine times cosine in there, which you would have to use substitution for. Or if you want to be fancy, you could use a double angle formula and then swap it with the double angle formula and then do an integration with a reverse chain rule. That would also work. So lots of ways. So we're here with that substitution. Limits of integration, remember, are reflected through your differential. So if our differential is dx, these are x limits of integration. When we convert to du, we also have to convert the limits of integration to reflect that variable change. And the way that we do that is by looking up here. That is how we exchange x's for u's. We plug in an x and we get out a u. So if we plug in the x equals 0 up here, cosine of 0 is 1. 1 minus 2 is negative 1. That's how we got this negative 1. Plug in the pi. Cosine of pi is negative 1. Negative 1, subtract 2, you get negative 3. So that's where we're at. Now we have a pretty simple integral. Right? This is a polynomial. That's the simplest type of integral. We can use that power rule thing where we add 1 to the exponent, divide by the new exponent, and then we will evaluate on the interval. So polynomial integration, add 1 and divide by the new exponent. That's the power rule for integrals. plug in so a couple ways here. You could factor out the 1/2 if you want. You can leave it in for each term if you want. So remember that constants can always be factored to the front, or they could be left in. Does not matter. Let's just leave it in this time. It doesn't matter. -3 squared is 9, so we'll get 9/2. And then subtract. So whenever we're evaluating with the fundamental theorem of calculus, we do the upper limit minus the lower limit plugged in. So antiderivative at upper limit minus antiderivative at lower limit. Plug in the lower limit, we get 1/2. So we're going to get 8/4, which is 2. So that will be the exact area between those two curves, right over here. The fact, did I subtract wrong? Oh, thank you. I could tell right away. I saw the face. I saw the face. I saw the face. So we get 4 units. Thank you. Thank you, thank you. And when you're looking at that shape, it's kind of interesting that you have an integer area with that weird trigonometric curve. You kind of expect to get something that was maybe irrational or, but getting an integer is probably not what we expected. Any questions on any of the steps? We all know how to subtract 1/2 from 9/2. Takes a little bit of work sometimes. All right. So these, again, are vertically simple because we're drawing vertical integration elements. Let's go ahead. Okay, so we're going to find the area here. I'll do the first one. I'm going to let you all do the second one. So let's do the first one first with this trig function, these trig functions. So find the area, and we have some limits that are given to us, limits of integration. So let's go ahead and graph first. It's always good when you're trying to find the area between two curves to sketch a graph. And here we're looking at sine and cosine, I hope. And if not yet, you need to be able to graph sine and cosine very accurately because we will be using those a lot. So I'm just going to draw one period of each. Pi over 4 and 5 pi over 4 are all in between 0 and 2 pi, so we don't have to think too hard, but we'll just draw a complete period. So when we're thinking about graphing the sine function, you should be thinking about these key points. So we have the 5 key points for sine. Generally, you don't need to graph the 5 key points when you're graphing sine because that one's just pretty easy, going from the x-axis back to the x-axis. Cosine, I find it's more helpful to draw the key points ahead of time. So the key points for cosine are going to form a V. And then we just have to connect the dots with curves. They're not lines. So this is going to come down like that, and then come up and do something like that. So there's cosine. So cosine is in red. Sine is in purple. And we're going 0 to 2 pi, so this is one interval of these two curves. All right. So now they give us these x values, and we're hoping that those x values have some really nice meaning here. And it turns out that they do. So let's just take a look at the unit circle. Whenever you see trig functions with unit circle angles, it's probably a good idea to draw a picture just to get a sense. If we think about these angles here, pi over 4 is right there. 5 pi over 4 is over here, right? 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. So these are the two angles. This is the first angle, and then that was the second one. Touchy, touchy. So those are our two angles. So what we know is that at pi over 4, sine and cosine are equal, right? So that's corresponding to this point of intersection right there. That is going to be pi over 4. It's where sine and cosine are equal, so their graphs will cross. Similarly, at 5 pi over 4 down in quadrant 3, Sine and cosine are both negative root 2 over 2. They are also equal. So that is going to correspond to this intersection point. So that intersection point is going to be at 5 pi over 4. So these limits of integration are super nice because they are corresponding exactly to those intersection points. And our goal then, finding the area, is to find that area that's trapped right in there between those two green dots. All right, so is this region vertically simple based on what we talked about a few minutes ago? Is it vertically simple? So the answer is yes. It doesn't matter where we draw our representative element, your representative rectangle. You can draw it wherever you want. The purple curve is always the upper curve, and the red curve is always the lower curve. So you can imagine that rectangle just sliding through the region. As you're integrating, that rectangle is just moving from left to right, and it's going to cover the whole region. And so now we can set up our integral. And the integral, again, it's supposed to represent an S for summation. You're summing. We're going to go from our left endpoint to our right endpoint. And then the rest of what we write down is going to represent the area of a rectangle. The area of a rectangle is the height times the width, or the height times the base, whatever terminology you want to use. The height of this rectangle is going to be a vertical distance. A vertical distance is always upper curve minus lower curve. Upper curve is purple, lower curve is red. So we are going to have sine minus cosine. So this is representing the height of the rectangle right there. The width of the rectangle is represented by the dx. So inside here we have height times width. There's the area of a rectangle, and we're going to sum them all up to get the area of the region. This integral we can do immediately. We know an antiderivative for each of those, and they're separated by a subtraction, so we can just integrate term by term. So that's going to give us the integral of sine is negative cosine of x. The integral of cosine is sine of x. So there is our antiderivative, and we will evaluate it on this interval, pi over 4 to 5 pi over 4. So we just have to plug in those limits of integration and do the arithmetic. So plugging in 5 pi over 4, we're down here in quadrant 3, 5 pi over 4. Sine and cosine are both minus root 2 over 2. So we're going to plug in, so for the 5 pi over 4 going in here, this is going to become minus root 2 over 2, and then we multiply it by a negative. This is going to become minus root 2 over 2, then we multiply it by a negative. So when that's plugged in, we end up with root 2 plus root 2. Root 2 over 2 plus root 2 over 2. Root 2 over 2 plus root 2 over 2. So that is the evaluation at the upper limit of integration. And then we subtract off, fundamental theorem of calculus says upper evaluated minus lower evaluated. So when we evaluate the lower at pi over 4, we're in quadrant 1. Both those values are root 2 over 2. So we're going to have minus root 2 over 2, minus root 2 over 2. But then we distribute this minus sign here, so we're going to end up with plus root 2 over 2, plus root 2 over 2. So we will end up with all of that. So we are going to end up with 2 root 2. That will be the area, the exact area between those two curves on that interval. Any questions on that one? So a lot of these Calc 2 things that we're going to do with integration are going to boil down to pretty basic geometry type things. So here we really are thinking about just finding the area of a rectangle. And then the Calc 1 that we're using is finding the antiderivatives of this, but the fundamental thing that we're doing is finding the area of a rectangle. That's the backbone of it. So let's talk about this one. I'll have you guys do the integration, but I want to talk about the graph. Let's set up the graph first, because we are going to see a lot of functions that have this kind of form here, this fractional exponent thing. And we don't need to be super uptight about the shape of this in terms of where the exact points it's going through. We just want to have a general sense. And the function that has this form that you're super familiar with is x to the 1/2 square root function. And you know it looks kind of like a bird wing, right? It just does that. And that's going to be the shape of every function that has a positive fractional exponent up here. Truly fractional, not like 3/2. That's going to cause a little bit of difference. But if it's a fraction, like less than 1, between 0 and 1, a third, a fourth, a fifth, a sixth, a tenth, 2/3, 2/5, 2/9, whatever, in quadrant 1, now some of them might have stuff happening over in quadrant 2 or quadrant 3 if you allow negative numbers. That's possible. Like if you have a 3 down here, you can have stuff over here. This says first quadrant, so we're just going to focus on the first quadrant. So all these functions that are x to a fractional power, they all look like bird wings. So we don't have to get super precise. We don't have to start plugging in, plug in 8 because it's a perfect cube. And you can plug in things like 8 and 27 and 64 or whatever, perfect cubes. But all you need is the general shape. Now, if we did allow negative numbers, which again in this case we're not dealing with negative numbers, but let's just talk about it just in case, would this function be defined at negative numbers? And the answer is yes, because if you plug in, just say -1, you would take the cubed root of -1 and get -1, and then square that and get +1. So the full graph of this is going to be symmetric around the y-axis. This will come down like that, and it's going to be symmetric. When you're dealing with a fractional exponent, 90% of the time you want to trigger the denominator first because it's going to make things smaller, and then you square it to make it bigger. So the denominator is always the root. So that's going to be the third root of x, and then whatever you get, then you square it. So in this case, we would have another side here. If this denominator was even, so a square root or a fourth root or a sixth root, you would get nothing on the left side of the y-axis because you'd be taking the square root or fourth root or sixth root of a negative, and we'd get no answer there. So the only way we're going to get something to the left is if that denominator is odd. Okay. But again, in this case, we don't really care about it. So then the second function is y equals 4. And again, we're just looking in quadrant 1, so we'll just do that. Bless you. So this says, one thing that's got to be true is that there can only be, we can't have ambiguity. And so there should be only one region that's defined by whatever the description is. Otherwise, it would be too ambiguous. So this says the region in the first quadrant bounded by these two curves. If you look at this little space right here, that's not bounded. Bounded means that you could draw a circle around it, the whole region. This region right here is going to be unbounded because it's going to go on forever. This region is unbounded because it goes on forever. So the region that is bounded by these two curves in quadrant 1 will be this triangular-ish region right there. So that is the only region that satisfies the conditions in the problem. So we're trying to find the area of that pink region. This region is both vertically simple and horizontally simple. We haven't gotten to horizontal integrations yet, but it is also horizontally simple. We'll talk about what that means in a minute. We're just doing vertical integration at this moment, and this is vertically simple, meaning no matter where you draw your element, you've got the purple curve on top all the way wherever you draw it, and the black curve on bottom. So now you guys find the area of that, now that we have the shape. Hoot and holler if you're stuck on any part of this. Yeah, yep. That is good. This is your upper curve. That is your lower curve. So this is the area of your, or the height of your rectangle, and then that is the width of your rectangle. Yeah. Good. Differential. Don't forget the width of your rectangle. Good. Visible ink here? That was dying. What is your upper curve?
Sorry.
That's all right. So when we look at this, so whenever we have a vertically simple region, one of the curves is going to act. So if you look at, once you've drawn your element, you have to ask yourself, what is the curve that's on top of that element and what curve's on the bottom? So the way I've drawn it up there, the purple line is your upper curve. Yes, exactly. And then your lower curve is that x to the 2/3 piece. Exactly. What is the integral for
Buzz. Oh, okay.
For x.
Okay.
Yes.
So that's the right idea, though, and then you find that would be whatever that is here.
Yeah. So you're going to integrate this. So first you have to have your limits of integration here, and then we integrate. So limits of integration, we have to take our two curves and set them equal to each other and figure out where the x value, what the x values are where they cross. And then we'll integrate term by term.
Yeah.
You want to take 4 and then square it? Or sorry, take the 4 and then cube it, and then take the square root of it.
Oh, did I do this backwards?
Yeah, you did that.
Oh, you're figuring out the crossing points?
Yeah.
Yep.
Qubit.
I'll start with that up here. Let's figure out where these curves cross because we need to know the points of intersection. And I've seen it on a few papers. If our goal here is to solve for x, we want to isolate the x, so we want to get x all by itself.
Thank you.
Whatever the power is on the x, we just undo that power by raising it to the reciprocal power. So we're going to raise both sides to the 3/2 power. And on the left side, that's going to reduce to just x. Because remember that if you have a power raised to a power, you multiply the exponents. So if we take a fraction and multiply it by its reciprocal, we get 1. So 2/3 times 3/2 is 1. So we have x to the 1, which is just x. That's one of the invisibles. If we have a 1 exponent, we don't have to put it on it. And then once again, we talked about this just a minute ago. If you have a fractional exponent, activate the denominator first, because that's going to shrink the number, and then you can cube it. Now, this one's small enough that it doesn't really matter. You could do 4 cubed and get 64, and then take the square root of 64 and get 8. Or, generally, the easier way is to take the square root of the 4, get 2, and then cube it and get 8. Doesn't matter, of course, in this case. It doesn't matter in any case. But it's usually easier to do the denominator first because it's making a number smaller. So that tells us that our intersection point is right here at x equals 8. So going to be this intersection point. And that's the only point where they intersect. We're told that we're in quadrant 1, so we know that this is right here at 0. The curves don't intersect there, of course. There's a gap between them. But that is our lower limit of integration. So now when we go to set up our integral, so integral symbol represents an S for summation. We're going to integrate from 0 to 8. That means we have rectangles all the way across from x equals 0 to x equals 8. We're going to find the area of each rectangle. Well, the area of a rectangle is the upper curve minus the lower curve to get the height, and then we multiply by dx to get the width. So upper curve is just 4. Lower curve is x to the 2/3. So that right there is representing the height of the rectangle. And then we multiply by the width of the rectangle, which is dx, so that's representing the width. So we get an area of the rectangle, and then we integrate term by term. So the antiderivative for 4 is 4x. The function that has a derivative equal to 4 is the function 4x. Or you can think of the power rule. Power rule even works for constants, right? What is the power on the x that's attached to this 4? 0, right? That's 4x to the 0. Add 1 and you get 4x to the 1. Divide by 1 and you still have 4x. So you can still use the power rule. That holds there. Here we do the power rule. We add 1, so we're going to add 3 over 3, so we get 5 over 3. Dividing by 5 over 3 means multiplying by 3 over 5. And our evaluation symbol, we go 0 to 8. Plugging in the 8 will give us 32 minus 3/5 multiplied by, plugging in 8 here. Again, simpler to activate the denominator first. The cubed root of 8 is 2, and then 2 to the 5 is 32. You could do 8 raised to the 5th power and then take its cubed root, but that's going to be a lot harder. So we'll do it the other way. We'll go the easy way. So we've got that. And now we just have to do this arithmetic here. Here is the approach I will use. I see a common factor of 32. Instead of multiplying 32 by 3/5 and getting a bigger number, why not do this? Factor out the 32, and then we're left with 1 minus 3 over 5. 1 minus 3 over 5 we can do in our head. 5 over 5 minus 3 over 5 is 2 over 5. So we have 35 times 2 over 5. No common factors between numerator and denominator, so this will be 64/5. That will be our total area. Make sense to everyone? Sorry. Any questions? If you can't formulate a question, you can just point and grunt.
Why doesn't this work?
Why doesn't this work? Because it's a calculator. 3/5. You better get better at fractions. The problem is you put in the wrong exponent. Operator error. That's the problem with these things. Is that not only do you have to, understand how to enter it, you have to enter it right. Did it work? Still didn't work? 96 over, let's see, so where did this 3/5 come from here? So this is, that's just this part of it. You still have this part of it.
Mm-hmm. But
So what you plugged in here is only part of it.
still, wouldn't it simplify to 3/5?
No, you're simplifying just this. This part here is 96/5 right here.
Oh.
But there's still the 8
Oh,
into
I
here,
see.
which
You
is
just kept the
32.
3/5.
Yeah.
Oh, okay.
Yeah.
I see.
The
I see.
3/5 is only attached to that 32.
Okay.
maybe I didn't point out this carefully enough. What is the evaluation of the lower limit in the antiderivative? 0, right? So it's minus, technically we have a -0 here. You obviously don't need to write that, but there is a subtraction of 0 for the lower limit.
How did you get to 3/5 x to the 5/3?
So the way we integrate it's not a polynomial, but it uses the rules of polynomial integration. We add 1 to the exponent and divide by the new exponent. When we add 1 to 2/3, we get 5/3. When we divide by 5/3, we get 3/5.
Okay.
We get the reciprocal. All right. Now that we have that mastered, let's go to horizontal integration. Horizontal integration, aka a horizontal integration element, a horizontal rectangle, sleeping rectangle. The rectangle's height is now sideways, so it's horizontal. So these regions are not vertically simple. Right? These are not vertically simple. So these shaded regions, if I draw this as a vertical element, and this as a vertical element, and this as a vertical element, clearly they don't have the same upper curve and the same lower curve, right? Not vertically simple for any of these. Vertically simple means that no matter where you draw your vertical element, black curve on top, purple curve on bottom, or whatever, same curve on top, same curve on bottom, all the way through. Clearly not vertically simple, but clearly horizontally simple. No matter where we draw that horizontal rectangle, same left curve and same right curve for all 3 of those horizontal rectangles. So that's horizontally simple. Same for this one. No matter where we draw this horizontal element, this horizontal rectangle, right, these are all horizontally simple. They all have a common left curve and a common right curve for those elements. So these get integrated with respect to y. I'm doing the same thing. We've got a rectangle. We're going to find its area, and then we're going to cumulatively add up all of those horizontal rectangular areas to get the total area. So the big difference is that the differential we use is the thickness of a horizontal rectangle, which is dy, instead of for a vertical rectangle, which is dx. So we're going to have a dy. We'll integrate with respect to y. The other big difference is that when we're doing a vertical distance, it's upper minus lower. Right, that's how you find a vertical distance. If you're on the y-axis at 10 and 7, this distance is 3. Upper minus lower. Horizontal, you do right minus left. If you're on the x-axis and this is 10 and this is 1, that distance is 10 minus 1, which is 9. All right, so here we're calling the right curve f, the left curve g, the right curve f, the left curve g, the right curve f, the left curve g. So that horizontal distance is f minus g. So right minus left. So when we look at this integral right here, we're thinking of this as the height of the rectangle, and this is the width. It's just that the height is horizontal. Sleeping rectangle. Lazy rectangle. All right. Let's take a look at this first example. Both of these functions are functions of y. So a function of y passes the horizontal line test in contrast to a function of x, which passes the vertical line test. We have a lot of symmetry here. Both these functions are symmetric about the x-axis. So this region is a region with symmetry. We could find the area of this upper portion and then just double it to get the total area. Or we could find the area of the lower region and double it. Or we could find the area of each region separately and add them together. So lots of things. In this class, symmetry is a really important part of integration. So I'll start by focusing on that and say, hey, let's just find the area of the top and then double it. Now, let's draw our representative element, our horizontal rectangle right there. And I didn't do this on the last problem, so I'm going to start doing this. When you think about your representative rectangle, you think of this as being located at a generic y value if it's horizontal. And it's not so important in these problems. It's going to become important in subsequent problems. Let me just go back for a second here. So when I think about this representative rectangle right here, I'm going to think of this at a generic x value. So I'm just going to call that x down there as we go forward. Again, it's not so important right here. But when someone says, well, where's your rectangle? Well, that rectangle moves. So we say that if it's vertical, it's just at a random x that's in the domain. Or if it's horizontal, we say it's at a random y that's in the domain. So we think of it as located at that generic point, x or y. And then y, of course, is going to range from, well, this is obviously 0, then up to whatever that y value is. So we're going to have these rectangles that are stacked on top of each other. We're going to sum them all up and get the total area. So let's go ahead and let's see if you can tell me what the equation of this upper line is coming from this absolute value function. So that is a function, but it gets broken apart. This line clearly has a different equation than that line, right? They have different slopes, so they have to have different equations. So what is the equation of that top line? X equals y. And what about the bottom line? Negative y. Exactly. So this is a piecewise defined function. A piecewise defined function has different definitions for each piece. So when you look at the definition of absolute y, the definition of absolute y, what it means is that it's going to be equal to y if y is greater than or equal to 0, and it's equal to negative y if y is negative. So that's the definition of an absolute value function. You just erase the absolute value signs if what's inside is not negative. And if you want to get the answer for the absolute value of y, when you're plugging in something that's negative, you multiply whatever is on the inside by -1, and that will make it positive. Right? So if you're taking the absolute value of -4, we know the answer should be 4, but how do you get to that 4? You take the -4, multiply by -1, and that gives you the positive 4. So you multiply what's inside. If what's inside is negative, you multiply by what's inside by -1. So there is the equation for this quadrant 1 piece of the absolute value function. Here is the equation for the quadrant 4 piece. Now we're focusing up here in quadrant 1. The area, so I'm going to call this area right here A sub 1. Call this one A sub 2, just to keep them separate and to make sure it's clear what we're writing down the area for. So the area in that upper portion in quadrant 1, it's going to be the integral. We haven't found our y values yet, so we'll get to that in a minute. Height of rectangle sideways, so height is right minus left. So that's going to be 2 minus y squared. Right? That is the function on the right, the black curve, minus the red curve. The function value for the red curve is y. So that is right minus left. That is the height. That is the width. And remember that we're integrating with respect to y, so this right curve is a function of y. The left curve is a function of y, so we should have all y's. We're integrating with respect to y. All right. Limits of integration. We want to know what that y coordinate is right there. We want to know where those two functions intersect, so we set them equal to each other. So we set the red, which is y, equal to the black, which is 2 minus y squared. So this is how we're going to find the intersection point. So we set the two equal to each other. We want to know what is the y value that gives us this common x value? All right, well, this is some more basic algebra here. Is this equation linear or non-linear? Linear or non-linear?
Non-linear.
Non-linear, right? Linear means that the power is 1 on all the variables. So that's clearly non-linear because there's a 2. So it's non-linear. And the rule that might not have been drilled into your head prior to this class will be drilled into your head in this class. Non-linear, everything to one side and factor. That's how you solve a non-linear. There are some exceptions where you can, extract the roots. There's some very small exceptions, but it will always work if you put everything to one side and factor. So that should be the first thing that flashes in your mind, like a pop-up blocker. Everything to one side and factor. So up here, everything to one side and factor. I'm going to add the y squared. I'm going to subtract the 2. Now we're going to factor. So we know that this will factor pretty easily. 2 times negative 1 is negative 2. We want to preserve a positive in the middle. That's going to be plus 2y for the inner, minus y for the outer. That's going to give us a plus y. And then the zero product property says that y is going to be negative 2 or 1. So which is it? Negative 2 or 1? We're up in quadrant 1 where y values are positive, so that y value must be 1. What does the x value have to be then? 1 also, right? Because here's our equation. If y is 1, x is 1. So this point is 1, 1. So that tells us our upper limit is 1, our lower limit is 0. Does the negative 2 have any meaning in this case?
Would be the lower intersection.
Right down here? If this one is positive 1, what do you think that one is? Negative 1. So what does that negative 2 mean? Quadrant 3? So if you extend this red line from quadrant 1 into quadrant 3, that's going to be where if this was extended, it would meet this parabola that's opening left, and that would be at y equals negative 2, which we don't care about in this case because we're dealing with quadrant 1, but that's what it would mean. So that's our solution, though, for this exact problem. Now we're integrating a polynomial, so we use the power rule for integration. Add 1, divide by the new exponent. So we're going to have 2y minus y cubed over 3 minus y squared over 2. And that's going to go 0 to 1. Plugging in 0 is a dud. That's not going to give us anything. All right, plug in 0, we get 0. So we really just need to focus on plugging in the 1. Plug in the 1, we're going to have 2 minus a third minus a half. We're going to get a common denominator of 6. This denominator there is 1, so we have to multiply that by 6 and get 12. We have to multiply that. Ooh. Yeah, I said that right. 2 times 6 is 12. Okay. So this one we multiply by 6 over 6. This one we're going to multiply by 2 over 2. So we multiply that by 2, we get a 2. Multiply this one by 3 over 3, we get a 3. So we're going to get 7 divided by 6. That will be the area of A1. And by symmetry, it will be the area of A2. And what will our total area be?
7 over 3.
So we're going to double it. We're going to multiply by 2. So total area will be 7 over 3. When you multiply that by 2, 2 will have a common factor with the 6 in the denominator, and leaving us with a 3. So total area will be 7/3. 7 over 6 plus 7 over 6. 14 over 6, which reduces to 7 over 3. Several ways to conceptualize it. Any piece of that you want to ask about? Any one of those steps? Is there any one of those steps that cause you pleasure? No, all right, well, tough crap. Only pain. Feeling only pain.
So was it necessary to do only the top portion of the area separate because it's intersected by the x-axis?
So we have to break it apart because this function is a piecewise function.
Oh, right, okay.
And there's no antiderivative for a piecewise defined function. You have to break it apart into pieces. So an absolute value function doesn't have an antiderivative.
If it were flipped onto the x-axis, would it be the same process?
Yeah, so if the absolute value function was y equals absolute value of x, we would do the same thing. We'd split it in the middle, right where that vertex is, and do area of one side, and then, yes. And if there was the same symmetry, then we would double it. All right, let's take a peek at that horrible shape. Terrible shape. Once again, not vertically simple. We have, if you drew your vertical element right there or right there, okay, they've got the same upper curve, but different lower curves. Right? So definitely not vertically simple, definitely horizontally simple. So we draw our element there, or we draw it here. Doesn't matter, left curve is always the red one, the right curve is always the black one. So horizontally simple. And if we want to, I'm just going to take this one out. We don't need two of them. So this is going to come across, and we're going to think of this as the horizontal element, integration element at y. So again, we don't really need that in this case, but we're going to start to think of that. Horizontal elements live at a random y, vertical elements live at a random x, which we will need when we get to the next section. Okay, so we need to find the intersection points. These ones are, well, maybe they're semi-obvious, but you cannot tell by looking at that graph definitively what those intersection points are. So we've got to do some math here. So let's set these two equal to each other. So we're going to set negative 2y squared minus 6y plus 30 equal to the other curve. It's always easiest to factor when you have a positive number in front of the square term. So I'm going to move everything to the right here. We'll get 3y squared plus 3y, subtract 30, so that's negative 18. We can divide out the 3, or a3. We can divide out 3 and get that. 0 divided by 3 is 0, so it's okay. You could just factor it out if you want. Doesn't matter. Divide it, factor it. It's gone. This is factorable once again. So we get y plus 3 times y minus 2. Double check. 3 times negative 2. Use the FOIL method to double check. Negative 6 right there. We get the y squared in front, and then the inner is positive 3y, the outer is negative 2y. That's going to combine to positive y. So zero product rule then says that y is negative 3 or 2. This setup up here, we have two curves that intersect in 2 points, and we got two solutions when we set the equations equal to each other. So that tells us both. So this y value here is negative 3. And this this y value here is going to be positive 2. So it's something positive 2. Now we don't need the x values here because we're integrating with a horizontal element. We're integrating with respect to y, so we only care about the y values. We could find the x values pretty easily, right? We would just take the y value and plug it into either, and then we get the x value. We don't need it, though, here, because we're integrating this way. So we only care about the y values. All right, so now you all do the rest of it. So you now know what your y limits of integration are. So see if you can set up your integral. and evaluate it.
But it's like what do it next to it. It's upper minus lower. What would it be? Just when it's right minus top minus lower. Gotcha. Cool. Thank you.
Yeah, what's the equation of integrating? It's this one, what is this one? Oh, the difference between the two when you integrate them.
This is so enjoyable watching everyone scribble math. Summer was so boring. I'm lying. Summer was not boring. It is when they let people scribble math. Remember when you're doing that right minus left, that you're going to have a minus sign that gets distributed across that second polynomial. Right minus left. Black minus red. When you subtract off red, you're going to have to distribute a minus sign. You keep writing. I'm going to start right now because there is a little bit of algebra here that I want to take care of. So that's what you should get up there once you do your subtraction of the two polynomials, right minus left. Anyone have a question up to that point? So we're looking at that integral on the board. That polynomial part is representing the height of the rectangle, and the dy is representing the width. Then for our integration, once again, we're integrating polynomials. So we can go with the add 1, divide by the new exponent model, the power rule for integration. So we should end up with that. Then we plug in the 2, plug in the negative 3, and take the difference. End up with something that looks like that before we combine all the individual constants. So I tried to call it out a little bit more explicitly here. This is the upper evaluation, this is the lower evaluation, and then we have the subtraction in the middle, which is going to have to distribute. I wanted to just call it out kind of this way because when you plug in a negative here, it gets a little confusing because there's a negative there, a negative there, and a negative there. So whatever you have to do to keep your minuses from exploding into something they shouldn't explode into. So then we end up with 22. And then here, there's a couple of shortcuts that I see. I'm going to use that technique I used just a minute ago. I'm going to factor out a 27. Do some algebra reinforcement here, some arithmetic. I'm factoring out 27. That's going to leave a 1 minus 1/2 minus 2. We factor out a 27. That we can do in our head pretty easily. So we're going to have 22 minus 27 multiplied by, so that's going to be a 1/2 minus 1, which is minus, 1/2 minus 2. It's a 1/2 minus 2, so negative 3/2. Negative 3/2. So that's going to be plus then. We're gonna triple that, so that's 90 minus 9, 81 over 2. Oh boy, lots of arithmetic here. 2. So 44 plus that. 44 plus 81. What's that? 121? That doesn't sound right, but you'll tell me if it's wrong. 40. Oh yeah, should be 5. Thank you. Yeah, 44. Yes. There we go. There is our area. A little bit of arithmetic there. Good to practice your arithmetic, but obviously, on an exam, you can just plug this into your scientific calculator. Go that way. But practicing arithmetic is good because a lot of times there's an X in there and it's not arithmetic anymore, then it's algebra and you have to combine it and you can't shortcut it. All right, any step there that you want to ask a question about? All right, well, question? Yes.
So suppose we got suppose we got like two really equations that are hard to visualize or graph.
Mm-hmm.
What's the right way to go about figuring which one's like?
So
the right one, which is
in
the
this
left one?
class, I guess it's possible if you were given these two and you didn't see the graph ahead of time, you might not know. On the exam, if you're given functions that you have to graph, they're going to be standard functions. If you look at the prior exams that I had posted, you'll see examples of those types of functions, things I would expect you to be able to graph. These are polynomials I would not expect you to be able to graph just cold. I mean, if you had plenty of time, hopefully. But though these would not be on an exam, if I was going to give you these types of functions, I would give you the graph. So things like that you absolutely should be able to graph, square root function. So square root of y equals square root of x, or a shifted square root of x, square root of, say, x minus 4 or something. Polynomials that are pretty simple, like quadratics and basic cubics. And the basic trig functions, sine and cosine. Absolute value function. So nothing too complicated. Yeah. Any other questions on it? All right, let's go ahead and take our 10-minute break, and then we'll do more math. And of course, I'm here during the break. If you have questions, you can ask during the break. All right, so these problems, both of these regions, well, it's one region. Both of these problems here are the same region, and you can do it either horizontally or vertically. Doesn't matter. I will do it up here vertically, and then I'll have you do it horizontally after we go through the vertical one, to show that we get the same answer. So I'm doing it vertically. I'm thinking of that as a representative rectangle, a representative integration element, however you want to think of that. And as soon as you draw that vertical rectangle, you're thinking the thickness is dx, so you know you're integrating with respect to x. As soon as you draw that integration element, that rectangle, you know whether it's a dy or a dx. Horizontal dy, vertical dx. Our area will be the integral. Height of the rectangle is the upper curve minus the lower curve. The upper curve is the square root. The lower curve is x cubed. So these are examples of functions I would definitely expect you to be able to graph. Those ones you should be able to graph. All right, let's see. Enzo?
Yes.
Okay. And Bradford? No. And you're not Anthony. Tegan? Yeah. Oh, yeah. So, again, those are examples of curves I would definitely expect you to be able to graph. Now, the limits of integration, you would set the curves equal to each other and solve. It's pretty obvious the intersection points here are 0 and 1. But I want to go through it just because there is some nuance here in figuring that out. Bradford?
Yes.
Yeah, okay, thank you. Just figuring out names still. It's going to take me a couple weeks. There's a little nuance here. So when we set these equal to each other, we've got a square root function. And hopefully it's sort of stuck in your head from college algebra that you isolate the square root function, then square both sides. So that's what we'll do. Nonlinear equation, everything to one side and factor. So everything to one side and factor. Well, we can factor out the x. And then we have that. And then we have the zero product rule that says if you have two factors multiplied together, one of them has to be 0. And this one has a solution of 1. The other one has a solution of 0. So that tells us that that x value is 0. And that x value is 1. So we will integrate from 0 to 1. Those will be our limits of integration. All right. Now we do the integration. This is x to the half, so that's going to be x to the 3 halves times 2/3. This is going to be x to the 4th divided by 4. 0 to 1. The 0 is a dud. Plug in 0 and you get 0. We're not going to get anything from that 0. We plug in 1. Plug in 1, we're going to get 2/3 minus a 4th. And the common denominator there is going to be a 12. So we're going to get 8 minus 3 over 12. We'll get 5/12. Assuming all the algebra is right. All right, any questions on that vertical process? All right. So, now you all are going to do this process. I want to talk about a couple of things here before I set you free. Turn into an arrow. All right, so this is random horizontal element at y. When you treat this as horizontally simple, your rectangle height is horizontal, so it's right minus left. When you are doing a right minus left scenario, you're taking the difference in the x values. Bless you. The way these functions are presenting is that they're presenting as y values. So we have to make a change. Up here, where we were doing a vertical distance, that's vertical distance is a change in y values. Well, both of these are presented as y values, right? We have y isolated on the left. So this is y equals, this is y equals. So they're presented as y values. If we want to do a horizontal, though, we need to change our perspective. We need to flip the coin and look at them as functions of y, in other words, as x values. So we need to come up here and change this to x equals, for the top function,
Y squared.
y squared. And down here, we need to change this one into an x value, cubed root of y, which you could write with fractional exponents or with the root symbol, either way. All right, so there you go. So now we've got the left and the right curves presented as x values. Now we can take their difference to figure out the height of the rectangle. So go for it. One third, the green one down there? Yeah, 1/3. It's y equals x to the third root of each side.
Yeah. I think we briefly touched on
Right at the end. Yeah. Right at the end. Minus left. Looks good. So when you're integrating that one, so we're adding one and dividing. Same thing here, add one, divide. Yeah, so y cubed over 3, yep.
You should add.
Same thing there, we'll add 1, so
Okay.
1/3 plus 3/3. Oh, look at your order here. So when we're doing, let me point it out up here. So this is going to be right minus left. So the y squared should be on the others. It should be flipped that way. Because this is left and this is right. So the y squared is the one on the left. So it should be the integration. Should be second. Okay, so the setup for your integral should be y to the 1/3, that's the curve on the right, minus y squared, which is the curve on the left. And then a dy. And these limits of integration look exactly the same as the prior, but are they? This 0 to 1 is coming from which axis? The y-axis, versus this 0 to 1, which is coming from the x-axis. So they have the same limits, but they're coming from different places. So this is saying that the y values are going 0 to 1. So here we're thinking of all these horizontal rectangles, 0 to 1 on the y-axis, whereas over here we're thinking all of these vertical rectangles on the x-axis, 0 to 1. Yeah?
The limits are only the same because the two functions together symmetrical about y equals x?
Exactly, yeah, it's because they intersect right at that 1, 1 spot, yeah. Now, they aren't symmetric about y equals x, though. Their intersection is symmetric, but if you were to draw the line,
Well,
you see what I'm saying?
yeah.
Yeah, yeah. Okay, let's rally for our last slide. Ooh, some more trig. Oh. Shocker. So find the area of the region described. We've got these two curves. Let's graph. So the first one, y equals sine x, that should be a pretty easy one to graph. If you want to put in your key points, you can. For sine, there's 3 points right on the center line. And then sine is up to the left, down to the right, and it's going to do that thing-ish. Okay, now the other one, the harder one. What type of function is that? It's a quadratic, right? If you were to distribute this, you would get x squared minus pi x. So that is a quadratic. What is the graph of a quadratic? Shape is what?
A u.
It's a parabola. Yep, U-ish. Parabola. Can you tell me what the x-intercepts are for this parabola?
Pi and 0.
Pi and 0, right? We can use the zero product rule. We've got multiplication here and multiplication here. So this tells us that x is 0 or pi. Those are the x-intercepts. So the x-intercepts for that function are 0 and pi, right there. Does this parabola open up or does it open down? Up, because the x squared has a positive coefficient. And we don't care where the vertex is. We're just trying to get relative shape. We don't know how far down it dips, and we don't care. What we do know from looking at this is that on this interval 0 to pi, green is always on top and red is always on the bottom. So that's all we care about. If we wanted to get precise with our graph, of course we could. But that's not what this is about. We just need to know relative position. The red is below the green. So regardless of whether that y, the y value for this vertex is -1 or -200, we don't care. Does not matter for us. So this is a vertically simple region. So when we draw a representative vertical element, vertical rectangle right there, that's going to be at a random x. There's our vertical rectangle. It's going to slide across the region. We're going to find the area of each of those individual rectangles and add them all up. So our area will be the integral. They tell us that we're integrating from 0 to pi. And we want to do upper curve minus lower curve to find the height of our rectangle. Well, the upper curve is the sine. It's the green one. Minus the red curve. And I'm going to multiply this out so we can integrate. So it's going to be minus x squared plus pi x. When we distribute that minus sign, that we're subtracting the second function, the lower function. So there is our integral. Again, this is representing the height, and this is representing the width of our rectangle. Let me know if you have a question on any of it. Integrating, we'll get negative cosine of x minus x to the 3/3 plus pi x squared divided by 2, and that's going to go 0 to pi. All right, so let's plug and chug here. We're going to plug in the pi first. So upper limit of integration goes in. Cosine of pi is -1. -1 times -1 is +1. So we're going to get 1 minus pi cubed over 3 plus, plugging in pi here, it looks like a pi cubed over 2. So So there's the upper limit of integration. The lower limit of integration, plugging in 0, these two terms over here are both going to be 0. So we're going to have minus a minus cosine, so plus cosine of 0. Cosine of 0 is 1. So there is our... So we can combine the 1 and the 1. We can combine these guys, get a common denominator of 6. So we can multiply this one by 2 over 2, multiply this one by 3 over 3. So we're going to have negative 2 pi cubed, positive 3 pi cubed, all divided by 6, so that's 1 pi cubed over 6. And that's totally fine to leave it like that. If you wanted to, combine those, you definitely can. Doesn't matter. Both of these answers are totally fine. If I can multiply properly, that's 6. Oh, that is 12. So that will be the area. All right. Enough of this 2 dimensions mumbo jumbo. Let's add some space. Let's jump into 3-dimensional space. 2 dimensions. Boring. Volumes. All right. So, Calculus 2 is mostly dealing with 2-dimensional problems, but we can do some 3-dimensional problems if there's symmetry and some well-behaved properties. Generally, to find volumes, you're thinking about Calc 3, where you're finding the volume between surfaces, whether it's this way, or this way. You have 3 different setups for volumes between surfaces. But we can use Calc 2 when our surfaces or our solid objects are well behaved. So let's take a look at this shape here. And if we take a cross section, we see that we've got a parabolic region as our cross section. And the idea is that we're going to take a cross section, get a parabolic region in this case, and then we're going to add a little volume to it and turn our cross section into a slice. So a slice is going to add a little bit of thickness or volume to it. And when we add up all of our slices, we get an approximation for the volume. And then as each slice gets narrower and narrower, the approximation gets better and better. And then we all know from Calc 1, that is a Riemann sum. This right here is area of the parabolic cross section. And then if you multiply it by a little thickness, that creates a slice. So you now have a mini volume. And when you add up all these mini volumes, you get your approximation. But then when you take the limit, you're taking the limit of a Riemann sum. The limit of a Riemann sum is a definite integral. So that integral right there is going to find our volume. That integral says that if we integrate the area function, and by area in this context we mean cross-sectional area, if we integrate the cross-sectional area, we will get the volume. Now that cross-sectional area has to be a continuous function, and it's got to be integrable. You can't have some weird function that you can't integrate. So notice that here we have area multiplied by width, which gives you volume. So similar type of setup before. On the inside before, we were adding up little areas to get a total area. Here we're going to add up little volumes to get a total volume. So the little volume is the cross-sectional area inflated with a little thickness to create a slice. So cross-section is 2-dimensional. Slice adds a little bit of volume, which is 3-dimensional. And this integral is now summing up a bunch of volumes from each slice. So every slice has a little bit of volume. We add them all up, we get the total volume. Okay. So we need a very nice, easily calculable slice, cross-sectional slice. A cross-section that we can turn into a slice. So a cross-section is two-dimensional, and it's got to be a nice cross-section that we can then turn into a slice. We can add a little volume to it. So if we look at this here, they tell us we've got this curve down in quadrant 1. So we've got the xy quadrant 1, which we would rotate up if we were trying to visualize quadrant 1 right there. And we're going to take these two curves, x equals 2 and the square root function. And what we have, we want to distinguish between the domain and the solid object. So the domain for our solid object is this region in the xy plane. So there's our domain. And then in our domain, we've got all of these squares. Squares right there. So we've got our domain. And you could put all sorts of shapes here. You could put triangles, you could put squares, you could put rectangles, you could put semicircles. So we've got our domain, and we're going to just start placing squares on there. So we're thinking about this is the domain, and that red segment right there, you're imagining this square, this red line is creating a square that's going to sit right on top of that. The red square that's sitting on top of that is this square right there. And if it's a square, do you see that the smallest square would be the one on the far right? Because this distance is the smallest in that domain. Right, that's only 2 units, so its square is going to be a 2 by 2. Whereas if we come up here to the very front, that distance is largest. So when it creates a square, it's going to create the biggest possible square. So that's going to be that end over there. Right, so your square is based on whatever the distance is between these two curves here, the x-axis and that square root curve. All right. So let's see if we can do it. So the volume will be the integral. In this case, they gave us, we see that the limits of integration are 0 to 2. We're going to integrate with respect to x. I've drawn a vertical element here. Anytime we have a vertical element in the xy plane, we're thinking dx. The thickness of that rectangle right there is dx. So we know it's going to be a dx. Now, so here is our random vertical element at a random x, right? So as x moves through, that little red segment gets longer and longer as we get closer to the y-axis. Can you tell me what the area of this rectangle that would be, the square, would be? This is representing the height. So here, that's going to give us the height of a rectangle, height of a square. Rectangle is a square. So what would be the area of the square that has this as one of its dimensions?
The height squared.
The height squared, the height's given by the function. Right? This function right here is measuring that height. And so if we say the base of the square is root 3 minus x, then this dimension has to also be root 3 minus x. So the area is going to be the product of those two, which is just the square of that. So this is going to be, whoops, I forgot to put the square root symbol in there. This is going to be the area of the square at x. If I tell you one dimension of a square is x, its area is x squared. If I tell you one dimension of a square is 7, the area is 49. Right, whatever that one dimension is, you square it to get the area of the square. So now we have an area function. That's our cross-sectional area function. And if we integrate the cross-sectional area function, we will get volume. You can think of this as area, this as the thickness or the width. That's going to multiply together to give you the volume of a slice. And then we add all those up and get the total volume. All right, so this simplifies pretty nicely. All right, you square the square root goes away, and we've got that. Very simple integral. Integrate 3 to 3x, integrate x to x squared over 2. Limits of integration 0 to 2. That is going to give us the volume of that, whatever that shape is described as. Plugging in the 2 gives us 6 minus 2. Plugging in 0, that's not going to contribute any volume. 0 in there and 0 in there gives 0. So we're going to have 4. And we weren't given units, but in your mind, you're thinking of 4 cubic units. We're thinking volume, not area. So 4 cubic units. So this is the general slicing principle. So if we have a solid object, and we can create a cross-section that is continuous and moves throughout the whole region, then we got it. So here, all the cross-sections are squares. So if we have something like that, we can find the volume. Let's try one that's a little different. So here we have a domain in quadrant 1. This looks kind of like a corner of an ellipse or something. So we've got that region, that's in quadrant 1. And now we have to be told what all the shapes are. The shapes all have to be the same. So let's see, what do they tell us? So they say, we've got this upper curve here. X-axis is that lower curve there. And we're going to rotate this. So we're going to rotate this around the x-axis, creating this parabolic solid right there. All right. So what is each cross-section then? If we take this and rotate it around the x-axis completely, each cross-section this way is going to be what geometric shape? Circle, right? And we're talking about a solid object, so more technically we would have a disk, right? We're going to have a disk for each one of those cross-sections. And we know what the area of a disk is. So in the last example, we knew the area of a square. The area of a square is the base times the height. What's the area of a disk? Pi r squared, area of a disk, pi r squared. So when we look at this, we've got this solid parabolic region over here. Isn't this red segment here the radius of the disk formed when you rotate that around the x-axis? So this function is acting like the radius of the disk at x. So that red thing rotates around and creates a disk. The radius is that function. So the area of the disk at x is going to be pi multiplied by the square root of cosine of x squared, pi r squared. So that function tells us the area of the cross-section at x. Let's check. Let's do a test to see if we're probably accurate. What would be the area of the disk when x is 0? Looking at this picture right here. When x is 0, we would be rotating around right over here. Now we imagine that disk. What's the radius of that disk? 1, because that distance is 1. So the area of the unit disk is pi. Now let's check over here at our formula. So we did that geometrically. We said, oh, we've got a disk of radius 1, area is 0. Area is pi. Now we come over here to use our formula. Plug in x equals 0. Cosine of 0 is 1. 1 times pi is pi, so it matches at this left extremity. Now let's look at the right extremity over here. What would the area of the disk be right there? 0, right? The radius is 0, so the area of the disk is 0. It's a degenerate disk. Let's check over here. Plug in pi over 2. Cosine of pi over 2? 0. Cosine of pi over 2 is 0. 0 times pi is 0. So our formula for the area is matching what we're getting geometrically by looking at these extremities. So we're probably on the right track. Now we can form our volume. Again, we have a vertical integration element, so that means it's dx. So we're going to integrate the area, continuous area function, multiplied by dx. And from looking at the graph of the domain here, we see we're integrating 0 to pi over 2. So that is going to give us the volume. This has a pi, which is a constant. It factors to the front. The antiderivative for cosine is sine. So we will have this evaluation to compute. 0 is, once again, a non-contributor. Plug it in 0, sine of 0 is 0. So we get no volume from that lower limit. We plug in our upper limit of integration, sine of pi over 2. So we're on top of the unit circle. The sine value on top is 1. 1 times pi is pi. That is the volume of our parabolic shape. So here we have pi. Again, you're thinking cubic units. We haven't been given the units, but in our mind, we're thinking of volume. So pi cubic units. So this right here is representing the area of the cross section. And this is going to be the thickness or the width. That makes sense? So let's see if this appy thing works. So if we look at this problem right here, we've got two parabolas, one opening up, one opening down in the xy plane. And then once again, we are going to put squares on top of the line segment that connects the two parabolas. So we've got our two parabolas, and we're going to create all these squares. It's going to create this funky looking shape over here. And let's see, here is the app that should help us visualize what's happening. It loaded earlier. All right, so if we come up here to the t values, you can sort of see that square all the way through. You can see these cross-sectional squares. You can see them a little more easily if we make these more transparent, less opaque. You can kind of see the squares as they move back and forth, right? All right, now this app, we can edit the upper and the lower curves. So we could make this exactly what we're dealing with here. The lower curve is x squared. This upper curve is, that's 2 minus x squared, is that what I'm seeing? And so now it's exactly, I think if I zoom in, it should let me zoom in there, but it's not. It's probably lagging. Where's that t value? There's t value. So this is exactly what we're looking for then. So we're trying to find the volume of this shape. We're going to do it by finding the area in general for that square and then integrating it. So we're integrating the cross-sectional area. All right. Ooh, why are you disappearing? There we go. All right. So let's find the area of the square first. We'll start with our cross-section. When we look here, we're going to have to do the upper parabola minus the lower parabola and then square it to get the area. So upper parabola is 2 minus x squared. So we have 2 minus x squared minus x squared. Everyone agree that that's going to be the length of that red line right there? It's the distance between those two parabolas. It's the upper curve minus the lower curve, so that should give us the distance between them. And then if we want the area of the square, we're just going to square that. Everyone okay with that? So then I think I've forgotten x squared somewhere, though. This is 2 minus x squared. So 2 minus x squared is the upper curve, x squared is the lower curve, so upper minus lower. This will give us 2 minus 2x squared squared. Let's factor out the 2. If we factor out the 2 here, we're going to have 2 factored out. It's going to be 2 squared when the square distributes. So we'll have that. Factoring out the 2, just because it'll be a little easier to FOIL this out. So we're going to have 1 minus 2x squared. No, yeah, plus x to the 4th. So we get that. So that is our area function at x. Let's figure out where these two curves intersect. And then we can check the extremities. The area at the two extremities should be 0. Where the two curves meet, the distance between them is 0, so we shouldn't actually have a rectangle or a square. So let's check. Where do these curves meet? So we're going to set x squared equal to 2 minus x squared. So we're going to get 2x squared equals 2. So we get x squared equals 1. So here is an example of a nonlinear equation where you can get away with not putting everything to one side and factoring. It will still work. It always will work. But you could use that special technique of extracting squares, or they call it extracting the roots. So we get x equals plus or minus 1. So that tells us that this x value over here is at positive 1. And this x value way back inside there is at negative 1. So at those 2 points of intersection, when x is plus or minus 1, we should end up with cross-sectional area of 0. Let's check. So when we plug in 1 or negative 1, it might be easier to plug it in here, actually. You can see here, if you plug in 1 or minus 1, you're going to get 1 minus 1, you get 0. Right? All right, so that means that our area function is probably the right function. And now to get to our volume, we are going to integrate. Could we use symmetry here? Could we use symmetry? Are these two parabolas symmetric around the y-axis? So one of them is y equals x squared, which, yeah, y equals x squared is definitely symmetric about the y-axis. The second one is y equals negative x squared, which opens down. That is symmetric about the y-axis, right? Negative x squared is just x squared flipped. And then we add 2, we just shifted it up. So if we have something that's symmetric about the y-axis and we shift it up, is it still symmetric about the y-axis? For sure. So we could integrate from 0 to 1 and double it. We could integrate from negative 1 to 0 and double it. Or we can just integrate straight across negative 1 to 1. It's not going to matter. Using symmetry is a good strategy, so let's go ahead and do it. So volume is going to be 2 multiplied by, and this I'm going to put a little note that that's because of symmetry. And then we are going to integrate the cross-sectional area right there. So that's 4 multiplied by 1 minus x squared squared dx. Oh, I already multiplied it out. I already multiplied it out. Let's use the multiplied out form because we have to integrate, so we need it multiplied out. So we got that. And because we're using symmetry, we're going to go 0 to 1. So that is going to give us our volume. The 4 factors out to the front. And then we're going to integrate that. So 4 to the front and then integrate. The integral of 1, antiderivative of 1 is x. And then minus, we're going to get 2/3 x cubed. And then 1/5 x to the 5. And that will go 0 to 1. Using power rule for integration. Does that 0 contribute any volume? So we can kind of ignore that because you plug in 0, you get 0. So we only need to deal with the 1, the upper limit. So we will have 8 multiplied by 1 minus 2/3 plus 1/5. Common denominator is 15. So we will have 8 multiplied by something with 15. This is over 1, so it's going to be 15 over 15. That one we have to multiply top and bottom by 5. That one we have to multiply top and bottom by 3. So whatever that is. 15 minus 10 is 5, plus 3 is 8. 8 times 8 is 64. We have 64 over 15. That has no common factors, so we are simplified. That is going to be our volume. Any step there that you want to talk about? So the main idea, find your cross-sectional area, multiply by dx, and then integrate. Cross-sectional area integrated gives volume. There is a pattern that we are seeing that maybe some of you have started to notice. Let me write it somewhere. Actually, bottom of this slide. So there is a general principle. Can you tell me the area of a circle? Can you tell me the circumference of a circle? 2 pi r. And we're going to do it as 2 pi r because of this. Do you notice the connection between these two? What's the derivative of the top one? If you take the derivative with respect to r? 2 pi r. If you integrate this one with respect to r, if you integrate length, you get area. That's what we did first. We integrated the height. We had the rectangle, we had the height of the rectangle, and then the dx was the width. Well, if you think about integrating the height of the rectangle, you're integrating that height function. If you integrate height, you get area. Same idea here. You're integrating this length, and we get area. So if you integrate a length function, you get an area function. What is the volume of a sphere? 4/3 pi r cubed. Not everyone knows that, but that is the volume of a sphere. And what nobody knows, until maybe right this second, is the surface area of the sphere. What do you think the surface area of the sphere is going to be?
4 pi r squared.
Yeah. If we take the derivative of this, we get 4 pi r squared. So if you integrate area, you get volume. If you differentiate volume, you get area. Yeah. So and no one seems to be able to remember that formula, but 4/3 pi r cubed seems to be a formula a lot of people can commit to memory. But so that's a pattern that we're sort of seeing. And right now we're in this scenario where if we know the cross-sectional area, we integrate that cross-sectional area, we'll get volume. And there's some basic geometric formulas that we see that follow that same pattern. Okay. We have a solid that's going to be created with these cross sections. So this piece of this section is general slicing. And for general slicing to work, we have to have a uniform cross section. So all the cross sections are squares. All the cross sections are discs. All the cross sections are triangles, whatever. So this says we've got a solid base right here. Comes from the function on that interval, negative pi over 2 to pi over 2. Cross sections we are now deciding to be isosceles right triangles with horizontal leg in the xy plane, with a horizontal leg in the xy plane. All right, so that's what they look like. Remember that an isosceles triangle has 2 legs that are of equal length. So what they're telling us is that these 2 dimensions are equal. So those are the same. All right. Let's maybe take a look at the area function for this isosceles triangle. So the area of a triangle, or cross section of a triangle, it's an isosceles triangle. So we could call both of these, if we want to use a generic letter, let's just use R. So the area of a triangle is 1/2 the base times the height. So 1/2, the base is going to be played by an R, and the height is going to be played by an R. So it's 1/2 the base times the height. So we get that for an isosceles triangle in this orientation. Everyone okay with that? So that's the area of our triangle. Now we're told that this R down here, that's root cosine x. So that's what's going to go in for the R up here. So we're going to have 1/2, and then we're going to have root cosine of x squared. So we are going to have 1/2 cosine x. That is going to be the area of the triangle at x. So if we plug in x equals negative pi over 2, or if we plug in x equals pi, this one's pi over 2 and this one's negative pi over 2. Pi over 2, negative pi over 2, we should get 0. Let's check. If we plug in pi over 2 or negative pi over 2, yeah, cosine of pi over 2 is 0. Cosine of negative pi over 2 is 0. If we rotate down 90 degrees, cosine is the x-coordinate, 0. So that matches. The biggest triangle should be when x is equal to 0. Exactly. That's going to give us the biggest biggest triangle. So if we plug in 0 here, notice, doesn't that give us the largest possible value for cosine on cosine's domain? Right? The biggest cosine can ever be is positive 1. And if we plug in 0 right here, so the biggest this area ever could be is when this function is as big as it ever could be, which is when x is 0. And that will be 1/2. That triangle will have an area of 1/2. Is there symmetry here? For sure. So this square root of cosine function is symmetric about the y-axis, so we could integrate 0 to pi over 2 and double it. We could integrate from negative pi over 2 to 0 and double it, or we could integrate from negative pi over 2 to pi over 2. So we'll use some symmetry. Our volume will be 2 multiplied by, we'll do the most intuitive one, which is 0 to pi over 2. And then we're going to integrate our function, which is representing area. And then when we put in the dx, that's inflating the area into a skinny volume, to a slice. And that integral is going to give us the volume. So the 2's cancel. We integrate cosine to get sine. We're integrating from 0 to pi halves. Once again, the 0 is not giving us any volume. Sine of 0 is 0. Sine of pi over 2, 1. So that is the volume. 1 cubic unit is the volume of that weird shape. You would never guess that that volume is an integer, but it is. 1 cubic, bless you, 1 cubic unit. Okay, so that was the general slicing method. And now some of you have seen what we're about to do before. So we're going to look at 3 different ways that are more specific. The only way the general method works is if every cross-section is the same. When we have things that are a little different, you can't use the general method. So we're going to have 3 techniques. We're going to look at cross-sections that are disks, cross-sections that are washers, and cross-sections in quotes that are cylinders. Kind of like Russian doll things where we're going to core and create cylinders that will fill up the whole solid object. We'll get to that. That one's a little less intuitive. So we're starting with disks. So the way we create and force all of our cross-sections to be disks is through rotation. And so we've already seen this formula once. It's just the area of a circle, area of a disk, pi r squared, where the r is given by the function. So here's a good example. If we take this triangle and rotate it around, we create a conical shape, a cone, which maybe some of you know the geometric formula for the volume of a cone. You could find it that way, but we're not going to do it that way. We're going to use calculus. So we've got this curve right there. We're going to rotate around the x-axis. That's going to be the shape that we're going to create. It's going to look kind of like this. So I created these guys in a very important free application that a guy I used to know pretty well created. He got an NSF grant. We used to go to conferences together 30 years ago. And he created this app from a grant that's called CalcPlot 3D. It's fantastic for Calc 2 and Calc 3 stuff. You can do all sorts of solids and whatever you want with surfaces. CalcPlot 3D, free app, really good application. So, for stuff in Calc 2 and Calc 3. So when this triangular shape is rotated around, it's going to create this cone. And what I did was took a cross section out so you can kind of see the disk. That red line right there rotates around. It's creating that disk, and I cut it out so you can kind of see what that looks like. So let's go through the math. So we know that our cross section is going to be a disk. So I'll always write the generic shape right there. Generic shape of the cross section is a disk. So area of a disk, pi r squared. Area of a disk, pi r squared. But in our particular case, the radius of the disk formed by this red line here, the red segment, isn't the radius just the function? 2 minus 2x? Right? That's the function. That's what the function is doing here, that function. So 2 minus 2x. That will be the area of the disk at x. So we've got a generic element at x right there. If we were to plug in whatever that number is right there, we will get the area of the corresponding disk. So let's simplify this function a little bit by, we've seen this function before. We can factor the 2 out. So when that 2 comes out, it comes out with the exponent of 2. And then we are left with a 1 minus x squared. And we do want to simplify this. We want to expand this, I should say. So we're going to have x squared minus 2x plus 1 when it's all expanded. Now it's in a form that we can integrate. So the volume will be the integral. We're going to have to figure out what the limits of integration are in a second. The 4 pi can factor to the front. So all we have to do is integrate this cross-sectional area function, and we will get volume. What are the limits of integration? So clearly 0. And then we need to know when that thing is equal to 0, what x value will cause that to be 0. And can you see it? 1. So this will be 0 to 1. So we would solve that by setting 2 minus 2x equal to 0. So this is going to be 2x equals 2, so x is going to be 1. So that point right there is at 1, that point right there is at 0. This will be the volume. We integrate, we get x cubed divided by 3 minus x squared plus x, 0 to 1. Once again, we have a 0 that's not going to contribute any volume. So the volume is equal to, plugging in the 1, we're going to have a third, minus 1, plus 1. So we end up with 4 pi over 3. Make sense? So You ready to try one? Any questions on any of the steps there? All right. All right, so what I want you all to do is set up the integral. And if you want to, you can keep going and integrate it, but at least get it set up. I want to make sure you can set it up. So the context is that we've got this exponential decay function trapped between 0 and natural log of 4. We're going to rotate that around the x-axis, creating this shape down here. Again, that red disk is that red line rotated around and then with some thickness to it. Some dx. Sprinkle in a little dx and your cross section becomes a slice. So see if you can set that up. So the cross sections are all disks, right? So the area of our cross section is nothing more than pi r squared. Everyone okay with that? You see that they're disks? Whenever you're rotating around an axis and your region is touching that axis, you're going to have crosses. They have to be disks. And the radius of this disk is the function. So we have pi multiplied by the function squared. So we have pi e to the negative 2x. So that right there is the cross-sectional area function. It tells us the area of the cross-section at x. Can you tell me what the radius of the disk is when x is 0? What is that radius right there? What's that going to be when x is 0? 1. And if that radius of 1 rotates around, it creates a unit disk. And the area of a unit disk, pi r squared would be pi 1 squared would be pi. And so if you plug in 0 into our formula here, do we get pi? Yeah, because we get e to the 0, which is 1, and 1 times pi is pi. So it's matching. And then our volume is just the integral of the area function. And they've given us our limits of integration, 0 to natural log of 4. And this reviews a little bit of what we talked about on Tuesday. That function right there is linear. We know that the antiderivative for e to the x is e to the x. But this is a modified e to the x, but it's modified in a very simple way. That modification is a linear modification. And so as long as we have a linear exponent, we can use the technique we talked about on Tuesday called RCR, reverse chain rule. When you integrate, you use reverse chain rule. When you differentiate, you use chain rule. And so let's see if we can do that. Pi is coming out as a coefficient. The general integration rule for an exponential The integral of an exponential is itself. Just like the general derivative rule for an exponential is it's itself. And then you have to modify it if the exponent is modified. So e to the negative 2x is itself. And now the modification, the tweak. We have to tweak it a little bit. What is the derivative of the exponent? -2. Divide or multiply by that -2. Divide for integration, multiply if it was differentiation. So we're going to divide by -2. So that is the tweak. And then the integration limits, 0 natural log of 4. Now we've had a bunch of antiderivative evaluation where when you plug in 0, you get 0. Do we get 0 here when we plug in 0? No, because we have an e to the 0, and e to the 0 is not 0. E to the 0 is 1. So let's see. I'm going to pull out this coefficient here. The pi and the -2, I'm going to stick those in front. So negative pi halves in front. And I'm going to treat this as the antiderivative right there. I'm going to plug in the upper and lower limit into that function and take the difference. So we're going to have e to the -2 ln 4. That's upper limit evaluation. Minus lower limit evaluation. We plug in 0. E to the 0 is 1. So we're just going to get a 1 there. So we have that. This is not simplified yet. There's more math that we can do. So we have negative pi over 2. Can you tell me what we can do with that -2? That -2 can be moved into the exponent position on the inside. So that can be moved into the exponent position on the 4. So we are going to have natural log of 4 raised to the -2. And what happens when we have e raised to a natural log? Right? They collapse. They annihilate each other. They're inverses of each other. So this will all become negative pi over 2. The e and the natural log cancel. We have 4 to the -2, which is 1/16 minus 1. So we have negative pi over 2. We're going to write that as negative 15 over 16. Now we get positive 15 pi divided by 32. No common factors. So that is our simplified answer there. All right, questions on any step? Everyone remembering from Tuesday the RCR idea? Okay, so it's really just an extension of the chain rule. It's just that when you integrate, you divide. The one caveat is that with the derivative chain rule, it doesn't matter how complicated the inside derivative is. Like if we have e to the 5x cubed, no problem. When you differentiate that, you get itself multiplied by the derivative of the exponent. Doesn't have to be linear, can be anything, multiplied by 15x squared. No problem. But when we're doing reverse chain rule, this exponent up here, for reverse chain rule to work, that has to be linear. So this will be e to the 5x over 5 plus c. All right, so reverse chain rule only works in that one special case, when the substitution is linear. All right, well, let's stop doing math for now, unless you want to stay for another 45 minutes. We can do more math. I will see you all on Tuesday. Have a good weekend. Week 1 of 15 in the books. Yahoo!
I had a question.
Yeah, absolutely.
How long do the recordings go up after?
It usually takes me 2 to 3 hours.
2 to 3 hours, okay.
Yeah, so I'll go right back to my office. I have to hit render, and that rendering, as long as I'm still here, I'll get it up within 2 hours.
Okay.
But if I have to go home because I have to leave or
No, yeah,
something,
just-
then it might be a little longer. But usually 2 hours.
Okay.
Yeah, usually 2 hours. It's ready to rumble.
How does the -2 get moved into the exponent on LM4?
Yes, great question.